All right, in this video, we are going to look over how to do test 3. So first problem, 1.73 moles of N2 gas. So that is N. Remember, every time you see gas, you first thought should be PV equals nRT. So the pressure is 1.42 atmospheres. The volume is 6.54 liters. What is temperature? So we have P, V, N, R. We don't have T. And what I'm going to actually do is I'm going to open up my equation sheet right now because I do not have these memorized. So let me pull up my equation sheet. And so R for this problem is 0.08206. So R equals 0.08206. So PV equals nRT, solve for T, which would be PV divided by nR equals T. And solve for T from there, putting in your values. As a reminder, your values will probably be different than my values because everybody has randomized questions for the most, or randomized values for the most part. All right, question 2, again, PV equals nRT. So I have 33.4 grams of O2 at STP. So we have to remember what STP is. STP temperature is 273 Kelvin. Pressure is 1 atmosphere. So we have a pressure, we have a temperature. We do have moles, but we're given grams. So we have to convert grams to moles, and we have R. So I'm going to put a squiggly above N because we kind of have that. So what's volume? We're solving for volume. So first we have to convert from grams to moles. So 33.4 grams of O2. We look on the periodic table and the molecular weight of O2 is 32. Remember, it's oxygen, 2 oxygens. Each oxygen 16, so 16 times 2 is 32. And we solve for moles there. So when we do that calculation, let me do that really quick here. Get my calculator up. We have 1.04 moles. And so now we just solve for V. V equals nRT divided by P. And again, fill in your, here, everybody had, I believe, slightly different amounts of O2, but you just fill in your values and solve for V. So that's question 1 and 2. Question 3, I more or less copy and pasted from our lecture. So I have 2 gases at very high temperatures in a container together. Gas A is 24, gas B is 53. What statement is true? And the statement that's true is the average kinetic energy of both gases is the same. Kinetic energy, the average kinetic energy for gases only depends on temperature. That's it. All right, question 4, I have 1.6 moles of neon, 1.13 moles of argon. What's the total? And the total pressure is 2.16. What's the partial pressure? So what you need to do, first off, is you need to find out how many total moles. So total moles is just Ne, moles of Ne plus argon. So total moles is 1.56 plus 1.13, which is 2.69. So then you take the moles of argon divided by total moles. So that's the mole fraction of argon. And you just multiply that by pressure to get the partial pressure of argon. So that's it. That's all you need to do. Question 5. Okay, so let's draw my system. If I absorb heat, heat's going into me, so that's positive 186. And I do work, that means work's leaving me, minus 98. What's my change in internal energy? 186 minus 98, positive 85. 6, I have two different metals. So metal A has a weight of, so let's do A and B. Metal A has a weight of 55.12 grams. Specific heat, so CS, of 1.24 joules gram centigrade. T initial is 87.42. B, mass. I don't know because that's what it's actually saying. What is the mass of B? CS, 0.768 joules gram centigrade. T initial is 58.89. So I'm putting these two metals in contact, which means we're exchanging heat. Temperature final for both is 61.39. Therefore, what's the mass of B? So the equation we need to do is the heat of metal A. So this is metal A. So heat mass, it's the heat of metal A equals negative heat of metal B, right? That is, any heat lost or gained by metal A has to be absorbed or released by metal B. And so Q, our Q, if you remember, Q equals MC delta T, or MCS delta T, where CS or C is our heat capacity. So let's fill this in for metal A. So mass of metal A is 55.12. CS of metal A is 1.24. Delta T is final minus initial, so 61.39 minus 87.42. This will equal negative mass of B, we don't know, so I'm just going to call that MB, multiplied by heat capacity, 0.768, multiplied by delta T, final minus initial, 67.39 minus 58.89. And we need to solve for mass of B. So one thing I did see a bit here is that people would report negative numbers. Again, this is one of these checks you need to do while doing these problems. Right? We're all humans, so we should be able to use our reason to see if this answer is reasonable or not. So when I'm asking, what's the mass of metal B? B can't have a negative mass. I can't say something minus 80 grams, right? So this should always have been a positive number, which means mathematically you just forgot that negative sign in front, right? So just keep that in mind moving forward, that when you get an answer, just ask yourself, like, does that make logical sense? Can I have a negative mass? All right, 7, when calculating heat, the value is negative if it's an endothermic process. That's false. It's negative if it's exothermic. 8, the higher the heat capacity of an object, the more energy it takes to heat it up. True. That's what heat capacity means, or one of the things it means. What does it mean that energy is a state function? So apparently a lot of people weren't listening to me or reading the slides. State function means path independent. Or we only care about final initial values. And initial values. That is, it doesn't matter what happened between our initial reading and our final reading. Like, the energy could have fluctuated a ton. All we care about is what is our final energy value, what's our initial energy value. Path independent, that's what a state function means. Okay, the number of times that waves pass through a stationary point, that would be your frequency. So frequency for 10. For 11, calculate the energy of light emitted per photon by a lamp with frequency 5.02 times 10 to the 14th. So just as a reminder, if I give you lambda, lambda is wavelength. All right. V is frequency. So the equation you wanted to use is E equals Planck's constant times frequency. And just figure it out from there, right? Planck's constant is, again, it's on your equation sheet. Solve for energy. That's it. Okay. A balloon is inflated from 0.336 to 0.625 against an external pressure of 11.87 atmospheres. How much work was done? So work equals negative P delta V. That's the equation. P is pressure, so negative 11.87 multiplied by delta V, which is change, which is final minus initial, 0.625 minus 0.336. But I am asking for work. So work is a unit of energy. So we're not done here. And I was actually really nice in that I gave you the conversion right there. So this is in atmospheres. This is in liters. So once you get this work number, you need to convert from liters atmosphere to joules. So you just take this answer and multiply it by 101.3 joules. All right, going from energy level of 3 to 1 releases energy. True. I think I skipped one. Yeah, so I just skipped one, question 13. So 4 to 2 releases energy. That's true. 3 to 1 releases energy. That's true. 4 to 8 releases energy. That's false. Every time you go down in energy, you release it. Every time you go up, you need to absorb it. All right, calculate delta H. So this is sum of moles products minus sum of moles reactants. Now I was nice here too. I gave you two values that were 0. So our product, the only product we care about is Al2O3. So it's 4 times negative 1710 minus now Fe3O4, 3 times negative 1391. And you solve for that. That's your answer there. 17. I have 3.3 grams of sucrose, molecular weight given. I burn it, my temperature changes. So bomb calorimetry. So again, it's the same equation as we saw above. Q equals MC delta T, right? For bomb calorimetry, Q bomb equals negative Q substance or reaction. I'm writing substrate. All mean the same thing. So whatever energy change you calculate in the bomb is just negative for your actual substance. Remember, when you blow something up, you're releasing energy. And if you're releasing energy, that means energy is negative. So let's take a look here. So actually, I got a little ahead of myself. For the mass, for the bomb calorimetry, we actually don't need mass because all we're doing is measuring water here. So it's just Q equals C delta T. So C of the bomb calorimeter is 5.87 kilojoules per centigrade, right? So that's the heat capacity. Then temperature final minus initial. Now, that's all. So in class, and this 3.3 grams, we actually never used this in this problem. So in class, I asked you for kilojoules per mole, and you would have to go the other step of finding how many grams of sucrose, how many moles of sucrose that is, and take your answer here and divide it. That's what we did in class. But here I'm just asking for kilojoules, right? And when you follow the units, which I'm hoping we all do when we do our calculations, we kilojoules divided by centigrade multiplied by centigrade. Centigrade cancels out. When you do this calculation, your final units are in kilojoules. So you're done. And that's it. And that's it for test 3. Again, if you have questions or you want to ask why I grade something, if you want to dispute something, please do send me an email and we can talk about that. Otherwise, good luck on test 4. And if you're watching this in the final, good luck for that as well. Catch you all in the next video.